generate negative resistance for AC signal. So, in impact diode for a typical let us say P plus I N plus, it is kept under reverse biased condition first of all. So, positive side will be connected to N plus region and electrons they will be accelerated and move towards the N plus region, and this N plus region for this typical P plus I N plus device, it is used for electron hole pair generation or for that avalanche impact effect. So, once electron holes pair is generated, then holes they will drift through I region and they will be collected by the P plus region. Now, there is a typical transit time to collect these holes, since these holes it takes finite time to traverse this I region. So, this transit time it depends on the length of I region. Now, this picture it shows a typical housing of impact diode. Usually impact diode itself it would provide capacitive reactance, and to nullify that we need some inductive reactance. It is usually obtained by using a bonding wire as shown by this magenta line here, and altogether they sits inside a cavity. So, you can see in right hand side picture how it looks from outside. We have arrangement for external biasing and we have the RF output from this end. Now, how this chain reaction it continues? Let us consider we have biased the impact diode by using a DC source and it is just near to the breakdown voltage. Now, we are sending some RF signal through the impact diode. So, in positive half of this RF signal, it crosses that VTH required for the breakdown. So, in the positive half cycle of this superimposed AC, breakdown will start, but it is delayed by a finite time. So, if I look at this picture, it shows the applied AC voltage versus omega t, and in the second picture it shows the electron hole pairs generation and the current due to that. So, when the AC voltage it crosses this 0 point, it is positive and the diode it is in breakdown mode. So, slowly electron hole pair generation it starts and it continues, and when the applied AC voltage it crosses the point pi, just after this it is this total superimposed AC plus DC, it is just below the voltage that required for the breakdown. So, then the electron holes pair generation it continues throughout this positive half cycle and it reaches a maximum point when this applied AC voltage it crosses this pi point. And now, after that it does not instantaneously stop, it even after that it continues to some extent, and due to that we have some more electron holes pair generation. So, at the negative most point of this AC it stops completely, and now once this electron holes pair are generated, these holes they drift through the I region and it will take finite time to reach this P plus region. So, if I look at the external current component, it would be exactly in opposite phase, and usually the length of the I region is so made that it will provide us another pi by 2 phase shift, or the current generated due to this avalanche breakdown it is exactly in opposite phase to the applied RF signal. So, RF signal then it can absorb energy from the avalanche breakdown, and that is how we can use impact diode as an amplifier. So, this right hand side picture it shows the equivalent circuit of that impact diode in addition to the housing. So, we have the capacitive diode effect and the inductive wire bonding, and also the effect of packaging. It is modeled by a parasitic resistor and inductor. So, diode terminal resistance, it depends on the series resistance, passive series resistance of the inactive region or I region, we can say. V d, the carrier drift velocity through I, L, length of the drift space charge region. So, I region, it plays an important role, its length, its resistance and the carrier drift velocity through it. Next, A, this is the diode cross section, E s, this is semiconductor dielectric permittivity, and theta is the transit angle. So, transit angle, it has one important relationship with R. R depends on transit angle. So, here we have a plot of negative resistance versus the transit angle. Transit angle, it is simply omega t, where t can be given by L by V d. L is the length of the intrinsic region. So, we see that negative resistance, it is a function of transit angle, and it is maximum when transit angle is equal to pi. So, it is almost periodic nature with decreasing amplitude. At transit angle equal to 0 and twice pi, it has minimum value. This is a photograph of impact diode typically used at 90 gigahertz band. Next is field effect transistor, MOSFET typically. So, in low frequency applications, we already know the equivalent circuit of MOSFET. It is a unipolar device, and the device characteristics is controlled by the applied electric field. But the problem is due to the capacitance, high capacitance value used as the oxide layer for the gate. So, we have to consider this capacitance effect at the high frequency, and the high frequency operation is mainly limited due to the capacitor. And not only that, inside MOSFET we have N type material and P type material. So, it is associated with PN junctions. Now, carrier mobility is highest in intrinsic material. Now, if we introduce some doping, so that means these foreign atoms, they behave as a scatterer, while carriers like electrons and hole, they move through this doped material, they will be scattered by this foreign agent. So, if we increase doping concentration, obviously carrier velocity will decrease. So, that is why inside P type or N type material, carrier velocity will be lower than that inside intrinsic layer. So, we will see there is another modification of conventional MOSFET, where we avoid this P type or N type material and we use simply intrinsic material for realization of the channel, and that is called the high electron mobility transistor or HEM. So, let us first discuss the basic operation of MOSFET and why its high frequency operation is very much limited. So, if I look at the characteristics, transfer characteristics and output characteristics, you see DS, drain to source current, it is a function of gate to source voltage. So, we can control the drain current by controlling gate to source voltage. And if we look at the output characteristics, VDS, it is if I increase VDS, there is almost no change in IDS. So, after this pinch off effect or in saturation region, we can represent a MOSFET by a current source, and this current value, it can be controlled by gate to source voltage, and below this region it behaves as a linear device, or we can replace the drain to source by a resistance. Okay, before, so this is a typical MOSFET device. You can see below is the body, and we have source, drain. Over that we have a thin oxide layer, and on top of this oxide layer we have gate layer made of metal or polysilicon. And if I now look at the frequency versus the FT and F max, realized FT and F max with year. So, in recent years there are conventional MOSFET, they have been developed, which for which the FT value is as high as 500 or 600 gigahertz. So, for that what we have to do? To increase FT, we have to decrease the transit time, just like BJT. So, we have to reduce the gate length. Now, even 10 nanometer technology is possible, and we have to increase the carrier mobility, so that transit time it decreases. So, for normal operation, so I will just a few basic points, so that we can go to HEMT and we can discuss the problem of basic MOSFET. So, when we do not apply any external biasing, in that case if we consider a NMOS, it starts with p type substrate, and we have N plus source region and N plus drain region, and since it involves PN, two back to back PN junction, at normal condition we do not have any current flow from source to drain. Now, let us consider a situation we have applied some drain to source voltage, but it is less than VGH minus VTH. VTH is the threshold voltage that needed to realize the channel in between source and drain. So, in this case one small inversion layer is created, and we have a thin conducting layer here, and we can represent the device by a resistance, or we have this linear region of this curve. Now, if I keep on increasing the drain to source voltage for a given gate to source voltage, then what will happen? We have this pinch up condition. So, we have this pinch up condition. So, once this pinched up condition is achieved, when VDS is equal to VGS minus VTH, this device it behaves like a current source. So, after that if we keep on increasing the drain to source voltage, the device current ID it becomes almost constant. So, this figure shows the cutoff frequency in terahertz versus gate length. This is the theoretical plot for double gate MOSFET and single gate MOSFET in different technology. So, in 10 nanometer double gate or dual gate MOSFET technology, you see the typical value is 3 terahertz cutoff frequency, whereas in 20 nanometer single gate MOSFET technology, gate length is 20 nanometer. So, typical cutoff frequency it is 1 terahertz using conventional MOSFET. Now, when we go for amplifier application, in that case the thumb rule is that if FT is given, we can easily use the device to FT by 10 frequency point. Now, you look at the electric field plot between the gate source and through oxide layer, this electric field it is associated with capacitance. So, we have a capacitor between gate and source, which can be represented by CGS, and we have another capacitor between gate and drain, which is represented by CGD. And in addition to that, we have body effect. So, in the equivalent circuit then, for high frequency operation, we have to add all these capacitors, one between gate and source, one between gate and drain. So, this capacitor registers inside the rectangular box, it shows the intrinsic device property. In addition to that, due to packaging and other effects, we have some additional capacitors, and that sometimes called the extrinsic model of the device. So, because of these capacitors, the gain of the device it becomes a function of frequency, and the frequency at which this gain becomes unity, current gain specifically, we call FT of the device. Now, for high frequency operation, one thing can be done, that we can decrease the gate capacitance. So, instead of oxide layer, there is one type of MOSFET where Schottky junction is used, simply metal semiconductor, we call it MESFET. So, you can see the picture here. So, just below gate we have N plus gallium arsenide layer. So, there is no oxide layer, and it will give lower capacitance, and we can increase FT of the device, but it is not very popular, it has some other problems. So, next we will move to a modified version of MOSFET, we call it high electron mobility transistor. So, as I discussed that if we keep on increasing the doping concentration, then the carrier velocity it will decrease due to the scattering effect of this foreign agent which are being used for doping. So, in HEMT device, typically it is a heterojunction device, two different types of semiconductors are used to realize this type of device. Here we used one intrinsic layer, and where channel it will be completely inside the intrinsic layer, so that the carriers, typically electrons, since electrons mobility is higher, we will prefer electrons as the carrier. It is much higher inside intrinsic layer compared to that doping layer, and that is how we can improve the mobility of the carriers, and that is why the name is high electron mobility transistors. So, some characteristics. This is a heterostructure field effect transistor. It incorporates a junction between two materials with different band gaps. So, that is why it is called a heterojunction as the channel. Commonly used materials are gallium arsenide with aluminum gallium arsenide. Indium it can give better high frequency performance, and gallium nitride it can give high power performance. So, in right hand side picture you can see a schematic diagram of a HEMT. So, below gate we have a thin oxide layer, and below that we have N type aluminum gallium nitride, and below that we have simply gallium nitride based carrier layer, gallium nitride based carrier electron layer. So, now how it operates? The electron concentration inside N type aluminum gallium nitride is much higher compared to the second layer gallium nitride. So, because of that we have bending effect and electron accumulation effect in the second layer. So, look at this band diagram. aluminum gallium nitride, it is a wide band gap semiconductor, whereas gallium nitride, its band gap is lower. At room temperature, the Fermi level, it aligns itself, and now at this transition point, this band, conduction band, it bends itself for continuity, and it bends deep inside the Fermi level. So, I am plotting the energy of conduction band versus x. So, x, it started from this top layer, and as x increases, we are going inside gallium nitride. So, just at this transition inside gallium nitride, the conduction band bends below Fermi level, and electrons in the conduction band of aluminum gallium nitride, it sees a lower energy states unoccupied inside gallium nitride. So, it will move to gallium nitride and it will be occupied by electrons. So, you can see inside the device, then we have electron diffusion initially from this n type material to gallium nitride, and because of that we have a very thin layer of electrons, and it will form a small depletion region here, and this will stop any further electron diffusion due to the built in electric field of this depletion region. The thickness of this electron layer is typically very small, just maybe tens of angstrom, and sometimes because of that we call it is a two-dimensional electron gas. Now, when some electric field is applied, so we have between electric field between source and drain, then mostly carrier movement, it is inside the gallium nitride layer, not inside the n type layer. So, that is how we can increase the velocity because of the increased carrier mobility inside undoped gallium nitride, and that is why it is called high electron mobility transistor or HEMT. So, it is being widely used at for different millimeter wave products, for satellite television receivers, radar equipments, etc. Now, when we use two different types of materials, they simply can't be placed one after another one. There is some problem due to their lattice, different lattice structure. When we use two different semiconductor materials, their lattice constant should be very close to each other. Otherwise, it will provide some loading effect, and because of that electron mobility again it will decrease. So, there are two techniques to avoid that. Usually, a very thin layer of one semiconductor materials is used on another semiconductor materials, so that thin layer of semiconductor materials, it stretches itself and closely follow the lattice formation of the second material. That is how we can obtain lattice matching, and the HEMT, due to that we call pseudomorphic HEM or p-HEM. There is another technique where another material is used, a third material is used as the buffer layer between this n type material and the intrinsic material. This buffer layer is used to match the lattice constant between these two layers, and this is called metamorphic HEMT or m-HEMT. So, we have two different types of HEMT devices, p-HEMT and m-HEMT. So, this picture it shows HEMT DC characteristics. Gate current, we still have some leakage current, gate current, but typically it is very small, but with the increasing gate to source voltage it increases, and of the order of a fraction of some microampere, and look at the variation of ID versus gate to source voltage. You can compare with the conventional MOSFET. At very high gate to source voltage, it is almost constant. This is the measured characteristics, and after that it follows nearly what we see for conventional MOSFET. And looking at the output characteristics, it almost looks like a conventional MOSFET device. So, it has the linear region and the saturation region. So, in saturation region, we can replace the device as a current source. Comparison of different solid state devices available in market. We are comparing breakdown voltage versus average cutoff frequencies in gigahertz. So, they are available commercially, and this yellow curve, it shows devices based on silicon and silicon germanium technology, and this blue one, it shows based on indium phosphide. So, if I look at the different types of this is showing high frequency and high power, high breakdown voltage means. So, in most of the cases HPT is the winner. Indium phosphide based HPT is the winner. So, after this we will see one application of active devices, that is electronic switch, but before that we take a short break. Thank you.